thing going in here are objects as well. We're going to start with a single object which represents nothing. And we're going to make a circle for that. An empty circle meaning nothing. Now later on it's going to seem an awful lot like 0, just to spoil it, but it's not 0, it's the name of something. You can think it's not an object 0, it's the name. So you might think of it as like 0 or 0 or whatever symbol you have, whichever language you prefer. It's the name of the symbol, it's not actually the symbol. So I could have just called it A instead, and A would be the name of the symbol, but we're using the same sort of symbol here. Okay. We also have one unary operator. You can take any object and it will return a new object. It is S. S is the successor object. So if I give you the number 0, what comes after 0? 1, that's right. The successor of 0 is 1. What's the successor of 14?
15.
Count in your fingers. What comes after 14?
15.
15. Yep. Right, you've mastered successor. That's all it's doing. It's saying what the next number is. What's the next number after 14 and a half?
15.
Kind of. There is no 14 and a half in our systems. Because what's the next number after 14? 15. There is no 14 and a half to fit in there. So that was, we're only dealing with natural numbers. We're only dealing with 0 and things that come after it in chunks. So we can't do 14 and a half. We can't do -1. We can't do pi. We can't do I. We have 0 and numbers that come after it. So this is quite a limited arithmetic we're doing. We still stay in primary school. No negative numbers or anything like that. Now, if we've got these numbers, what sort of things might we be doing with them, given we've only got positive whole numbers? What sort of operations might we do in them? Generally, you're in a 7 or 8-year-old. Sorry? Yes, or plus them, as I used to say. So we've got a plus symbol, which represents addition. You can add two numbers together. And if there's two positive numbers and you add them together, you're going to get another positive number, so that's fine. What else might you do?
Subtract them.
If you subtract them, that seems like a good thing. But what if you subtract one number from another? Will you always get a positive number? So that's a dangerous thing. So it's too hard. It's only stage 2. We're going to chuck away addition, subtraction. Subtraction is just too hard and risky for us. We covered that briefly in stage 3, but that paper got dropped because the maths department claimed it was too technical. I kid you not. Okay. They claimed that their maths students couldn't handle the maths in a stage 3 philosophy. We introduced things like minus, just thoroughly. So that's the sort of thing, but it's actually too hard. What else might we do? If we take numbers in, we get more numbers that are also positive.
Multiply.
Multiply, yep. Multiply is safe. Now divide, you can sometimes get numbers like a half, which are tricky. And exponentiation is just way too hard. Again, we do that in stage 3. So these are all we're going to be doing. We've got this thing that I will occasionally call 0, but I shouldn't. The successor function, which gives you the next number. And the plus and times, which are going to be a lot like our plus and times. So we're introducing these new symbols to our system. Okay, let's write down, so let's have something hard. 1 plus 1 equals 2. That's what we're going to write down, and then we're going to try to prove it. Just to get used to the system. Okay. So you guys want to try to write down 1 plus 1 equals 2? No, some of you are shaking your heads. Okay, I will do it, because obviously this is advanced mathematics. Okay, so I don't put one symbol, but I do the 0 symbol. And 1 is the next number after 0. So I've written down 1. Plus 1. Now that's a function, so I'm putting brackets around it. Same as and or and like that. So 1 plus 1, put together then, equals, now I want to write down 2. Now 2 is the next number after 1. 1. So 1 is the next number after 0. So 0. Next number after that, next number after that. So 1 plus 1 equals 2. Now, that's how we would write this in our language. You've now kind of mastered the language of arithmetic. It's just going to be this. You just write down enough S's till you're happy. How many S's do you write down? Well, if you want to write down 17, you write down 17 S's and a 0. We won't be doing many questions with 17 in it. We did have an exam once where we had the number 6 and people thought it was a bit long, so we tend to keep our exams with numbers smaller than 6. Okay, so who thinks this is true? So who thinks that in normal arithmetic the meaning of the sentence is true? Who thinks 1 plus 1 equals 2? Yes, people are more confident, okay, but I told you we're doing primary mathematics. Let's prove it. So that's number 1. What's the main connective? It's an equals. So we're going to do equals introduction. And that comes from a block. So now I'm just going to rub this out. This is just showing how to fit it in. And this is going to be my block of reasoning above the other bit. Right. This is line 2. And like any equals block, we do an assumption. It's got the lines above and below. We want to say our first side of our equals at the top and our second side of the equals at the bottom. We want to do a number of steps in between to get there. So, and we're going to give reasons for each of these as we follow the steps. Now we've got a problem because we have no premises. Yeah.
Just on a semantic thing, are we allowed to write to equals introduction? Or 1? Because it's going to be below it in the proof, isn't it?
That is the proof statement.
Oh.
Yeah. So we're working up from the conclusion. It's just that I'm doing it the other way around because slidey boards and confusion. Okay, so yeah. Sorry, I should have made that explicit. The 2 is above the 1. Now, to do any steps, we need some sort of rules. We don't have any premises to use, but we know how numbers work, right? So what we're going to do is introduce some definitions that describe how numbers work. There'll be really little steps of definitions so they can apply to all numbers. And then we can use them in here like premises. So, when we came with these symbols weren't just added to the language, we also got some rules to go with them, some definitions. And these are those steps that we will use. There are 7 of them. And I know the first 6, so I need to look up the 7th one, because I do not like it. I always forget it. Q1. Nothing comes before 0. For all x, the number after x is not 0. 0 is our smallest whole number. So our first rule is there are no negative numbers. This also stops you from saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0. 0 doesn't come after 11. You can't do clock arithmetic, which is useful in digital clocks, but not here. There's no biggest number after which it like overflows and resets to 0. You don't have circular arithmetic. You can remove that rule, you get really cool stuff. But you learn that to standard 3, and we're not quite there yet. Clock arithmetic. We'll get to standard 3 in an hour or so. Okay, here's the next one. If I've had 2 numbers, and the successor of this number is the same as the successor of this number, they're the same number. So if I know that the one after this is the same as the one after this, then they are the same number, so I can reason backwards. So Q2, I'm going to run out of room here. For any 2 numbers, if the number after each of them is the same, then those numbers are the same. So we take 2 big numbers and reduce them bit by bit to something that's simpler. So it's making things simple, and then eventually we'll get down to 0. Okay, so this is all we need to do to manipulate numbers without adding or anything like that. From this we can tell if 2 numbers are the same or not. Okay, let's just use those 2 as an aside before we can finish this off. Let's say I claim that 3 equals 2. Now our system, maybe this is true in our system. Now by Q2, if I just take the S of each of these, then by Q2, then that means that S of O equals S of O. If S of this is equal to S of this, then this is equal to this. So that's by Q2. Notice we're taking some shortcuts. We're just writing down the definition of the rule we're using. We could spell it out if we needed to, but we're assuming it's reasonably obvious. This is our definitional shortcut. Now, SSO equals S of 0. That means that S of 0 equals 0, again by Q2. We're knocking 1 off the end of each of them. And now Q1 tells us any number you choose, S of that is not 0. So, but S of 0 is not 0 by Q1. And our not 0 is the same as writing not is 0. So if we thought 3 was equal to 2, we've proved a formula and its contradiction. Bam. 1, 2, 3, 4, 5. This comes from 3 and 4. So if you think 3 equals 2, you can prove a contradiction. Which of course, 3 is not 2. That's my conclusion. So we didn't do any maths yet, but just see how those two rules can be used to prove useful things like 3 is not 2. Okay, not that useful, but okay. Any questions on how we use these rules here? I guess I should be a bit careful and say that came from line 1, that came from line 2, that came from line 3. Now I've added line numbers. It's the same sort of reasoning. We broke it down to simpler things. Basically said, if 3 is 2, if 3 is 2, then 2 is 1, then 1 is nothing. But 1 is something. Something can't be nothing. That's nuts. So 3 is not equal to 2. That's our reasoning. So now you have proof that 3 is not equal to 2, which you've been taking on faith for the last 20 years. Let's do something slightly more useful. Okay. We're going to introduce rules for addition now. Can I rub this out? People are happy 3 is not equal to 2. Another thing you can go home and tell your parents that you've learned. This is good. Okay. Q3. For any number at all, x plus 0 equals Sx. 0 plus x? Well, way too hard. We're going to be proving that somewhere near the end of next week. X plus 0 equals 0 plus x? Hard. Okay, x plus 0 equals x. Adding 0 makes no difference. So now we can add 0, which is really useful. What's the other sort of number? It's not 0, it's going to start with an s, right? So what is x plus some sort of other number? So for any x and for any y, you're going to need a way of adding numbers that aren't 0, because it's even more useful than adding 0. X plus s of y. It's going to be x plus y, which you can add, and what else do we need to do for that? Sorry? We add s, yep. So x plus 1 more than y is 1 more than x plus y. So when we got x plus y, we can work out x plus the successor of y by adding 1. So if we go to big numbers, we can break those down to simpler numbers. So again, I'm going to do a worked example of how this might work. Let's say we want to know that 3 plus 2, which I guess we should write out as SSSO plus SSO. This is all equals reasoning, so this will be inside some sort of reasoning block. This is just an example. Okay. Now, by this rule here, x plus s of y is equal to this, which is s of x plus y. So I've used Q4 to break down the bit inside the brackets and simplify it. Now I'm going to use Q4 again. Here's my x, here's my y. S of S of S S S O plus O, Q4. So 3 plus 2 is the same as 1 more than 3 plus 1, which is 2 more than 3 plus 0, which is 2 more than, well, 3 plus 0 by Q3, 3 plus 0 is 3. Now, those brackets kind of show you what you need, but the brackets don't do anything, so I'm going to remove those brackets. 5, 3 plus 2 equals 5. From 2, by identity introduction, 1, done arithmetic. No, it's right. 3 plus 2 does equal 5. Don't you?
Yeah, no, but
Sorry.
why did you just only change the second bit, not the first bit? I mean,
Why did
that's
I change?
slower.
Why did I change this and not that?
Yeah.
Right. Okay. So this is an important restriction. The S is on this bit.